For the MOSFET shown in the figure, the threshold voltage Vt magnitude is equal to 2 volts, which means the threshold voltage of NMOS is equal to threshold voltage of PMOS, but of course magnitude is equal to 2 volts. And K is given, which is half mu Cox W by L equal to 0.1 milliampere per volt square. The value of ID in milliamperes is dash. In fact, ID is shown here. Now, in order to find ID, first of all, we have to find which modes the transistors are functioning in. To start with that, let me just say this is M1 NMOS, this is M2, which is PMOS. So for M1, VGS will be equal to, gate voltage here is 0 volts, but source voltage is minus 5. 0 minus of minus 5 volts is equal to plus 5 volts. Obviously, this is greater than the threshold voltage 2 volts. M1 is going to be on. And let's come to M2, in which case to find the voltage at gate. To find this, we have this voltage divider network, 10 kilo ohms and 10 kilo ohms. So the voltage at this point will be equal to 6 volts. As the voltage divider is going to divide the voltage equally, then VGS for PMOS is going to be VG is equal to 6 volts minus Vs is 12 volts. So we have minus 6 volts. We are always interested in the magnitude of this, which will be 6 volts. Obviously, even this is greater than the threshold voltage Vt magnitude 2 volts. Obviously, if both the transistors are supposed to be in saturation region, given that K is same for both, it is not possible, because if we have to have IDP magnitude is equal to IDN, then as mu Cox W by L times half is equal, then VGSP minus VTP whole square should be equal to VGSN minus VT whole square. In this case, VGSP magnitude should be equal to VGSN, which is not correct, which means both the transistors cannot be in saturation region. So let me put a table here that M1 and M2, saturation and saturation is not possible. And let's say both of them in linear and linear. We know the voltage across these two transistors, VDS, is 12 minus of minus 5 volts, which is 17 volts. So VDSP magnitude plus VDSN magnitude should be equal to 17 volts. If both the transistors are in saturation region, this should be less than 4 volts and this should be less than 3 volts, which means overall the sum of them should be less than 7 volts, which is not possible because the voltage across the two transistors is 17 volts. So hence, even both being in linear region is not possible, which means one of them can be in linear, one of them can be in saturation region. Now the question is, which one should be in saturation and which one should be in linear region? Now if you look at this, as both the transistors have similar characteristics like Vt and K, only the VGS is different, but the current to flow through two transistors is same. Which means if we assume M2 to be in saturation region, that current cannot be supported by M1 because VGS is smaller. But when VGS for M1 is smaller, it allows small current to flow through, which is corresponding to 5 volts of VGS. It can easily be supported by M2, but of course M2 has to be in linear region to support it. So that's the only possibility we have, where M1 should be in saturation region and M2 should be in linear region. In that case, we can write the current equation ID is equal to mu Cox W by L times VGSN minus VT whole square over 2. Now this entire term is 0.1 milliampere per volt square times VGSN is 5 minus VT is 2 whole square. This is equal to 0.9 milliamperes. So the current ID will be equal to 0.9 milliamperes.